Hello everyone. Um, okay, so this is a live tutorial session for the NPTEL course on Theory of Computation, and I'm Neha. I'll be one of the TAs for the course. So I think there's one more TA, Krishna, and so my name is Neha, and just to give you a brief introduction about myself, I'm doing a PhD in theoretical computer science at the Department of at IIT Madras, and I'll be one of the days for this course, and we'll have our sessions on Mondays from uh, 7 p.m. to 9 p.m. And I think this is a 12-week course, so we'll have 12 tutorials. And so as of now, this slot is frozen, but um, okay. And I think that's all about myself. And just to give you a little bit of overview about what this course is all about and what sorts of prerequisites do you need. So one prerequisite for this course is the foundational course on discrete maths. So this is because we'll need a lot of notations and concepts like functions, sets, logic, and so on. So we'll be using this back and forth. So if you're not familiar with this, then I would suggest to go back to this course first before starting off with this. And any basic course on algorithms is not a prerequisite, but this is just advisable. Okay, so okay, so this is just I would just suggest basics of this, but you don't need to know. It's not a prerequisite as such, and I think that's all. Um, yeah, okay, and so just to give you a brief outline of what this course is going to be about. So, um, I'll. Is this fine? Is this visible now? Okay. Okay. So, what this course deals with is what is called models of computation. Okay. And so given any problem, given any computational problem, what you want to do is you want to, let's say, design an algorithm for it. But um, yeah, but we'll be talking about what kind of model do you use. So modern day algorithms are equivalent with what are called Turing machines. If you don't know what these are, that's totally fine. But for those of you who know, I guess you can connect to this. And these are very powerful models in the sense that uh, all the computers that we have today are captured by this model of computation called Turing machines. But before we had this model, if we restrict ourselves to, let's say lesser memory or lesser power, okay, then what kind of computations can we do? So there are one model that you have started up with this course is what is in this course is what is called deterministic finite automata. Okay, and we'll see few more models such as push down automata and so on, and we'll see why one is more powerful than others and what does it mean to say that one model is more powerful than the other. So how do you compare? Okay, and second question is, uh, what can this model compute? Okay, so what are the limitations of these models? Okay, So whatever we do, whatever we build up in this course will be around these, more or less around these two central questions. One is, when we introduce a model, you can always define a model of your choice. These are just standard models that we stick with, but you can always come up with your own model. And now once you have this, we want to compare this. So this will be one of the central questions around which the course is built. And the second is, uh, if it cannot compute everything, then we want to understand its limitations. We want to better have an understanding. Okay, and although these two questions right now are very abstract because I have not defined what a model is and what do we mean by comparing and so on, but this will get more concrete as we go along the course. Okay. Okay, so are there any questions at this point?
So, what could be the meaning of proposing our own model of computation? These models are fine, but then as far as the models are concerned, there are alternative models being indicated, like say lambda calculus, cellular automata, and it is also mentioned that these models are Turing complete. So, what would be the meaning of proposing our own model of computation?
Okay, so okay, so um, if you're familiar with DFAs, okay, um, so what one could do is, so you know that in a DFA, you are only allowed to move to the, like, given a string, let's say 101, you are only going to go ahead, right? You, once you have read a 1, you won't be able to read it again. That same, okay, let me just admit a few people. Okay, so okay, maybe let me do one thing. I'll define the model. So first of all, and then I'll come back to your question. Okay. Yeah, so let me start by recalling the definition of a DFA. Or okay, so this is defined as a five tuple. Okay, so this queue is the set of states that you have. If you have seen the picture, then I'm just drawing one possible. Um, okay, so if you have seen this picture, then the set of states q here will be q0, q1, q2. So you have a set of states that are fixed. Then sigma is the alphabet. So in this case, 01 is the alphabet over which we are working. So this corresponds to how the input is given to you. If the input is given in binary, then in this case, for example, sigma is 01. And typically, if nothing is, if nothing is mentioned about sigma, then the assumption is always that it's a binary alphabet. Delta is what we call the transition function. This is alphabet, and the transition function is defined as follows. Given a state that you are in and a letter an alphabet that you read, it tells you where, in which state you should go. So for example, if you are at q0, so that is your q, and if you read a 0, which is one of these sigma, then it tells you where you should go. Okay, and it's complete in the sense, no matter what state you tell me and no matter what alphabet you tell me, there is always going to be some q in which it should land, so it won't be stuck. Okay, and f is the set of final states. This need not be unique. So for example, I could also make q1 as my final state. So this f is a subset of q. In this case, f is q1, q2, and q0 is the start state. Okay, so this arrow here tells you which is the start state. In this case, it's q0, And when do we say that DFA accepts a string? I mean, feel free to answer. I know it's a simple question, but
Oh, did you ask something? Yeah.
yeah,
So
yeah. I said, when do you say that the DFA accepts a string?
so the strings, like, see, in this case, I mean, all the strings which are starting with a zero, I mean, even this will accept zero, and then zero followed by any number of, I mean, either zero or a one. So in fact, it will accept all the strings and which are in fact, this will also this will accept a string having at least one zero and followed by any number of the zeros and doubles.
Yeah, correct. That is, yeah. So for this automaton, the language that is accepted, if this is M, then the language of M is zero followed by um, zero one star, or in other words, it is zero W such that W is in sigma star. Okay, so yeah, but I mean in general, so it is, I mean for this example, this is the language that we have, but in general, when do you say that a machine accepts a string? Or
Uh, Means like we say when it doesn't end in a non-final state, means when the last symbol is red and it is in means like it is not in final state, not in final state, then it is rejected. So otherwise it
yeah,
is accepted.
correct. Yeah, good. So you say that M accepts a string X in sigma star if and only if M on X reaches one of the final states. Yeah. So yeah, so this is the notation for if and only if any of you is not familiar. Yeah, and yeah, at any point of time, if you have any questions, feel free to stop me and ask. Okay, so yeah, so this is the basic model that we all know. Okay, and to
I have
make,
a question.
yeah, sure.
What is the real world application of accepting or rejecting a language?
Okay, good. Okay, so okay, so I'll give you an example. So you might have some familiarity with writing program C or I mean any language is fine. So let's say for example I give you a problem which is that given an input, if that input, let's say it's in binary, if that input is an even number, then you are supposed to accept it, and if it's odd, then you are supposed to and basically you have to detect whether the number is even or odd. Okay, so you can come up with an algorithm for it, and you can write a program in any language of your choice. Okay, so let's say you have this algorithm. Okay, and which is basically a set of instructions. Okay, then um yeah, then this uh, I mean when you write it, it's in the form of an algorithm, but when you run it, you have a notion of a machine, right? So this machine takes as input um, a string x, and tells you whether it's supposed to be accepted or rejected. Okay, so okay, so uh, so what are the kind of strings, if I write it in terms of a set, what are the kinds of string that will end up being accepted? So let's say the program is to find up an even, check whether the number is even. So can you tell me what kind of strings will end up here,
2, 4, 6, 8, etc.
etc., right?
Ending with zero.
um I think I couldn't hear the last
Ending with zero, binary string ending with zero.
Correct, correct. So if you write it in terms of binary, yeah, so the input is in binary, so anything, um, yeah, that ends in 0 where W is a uh, binary string. Okay, so yeah, so no matter what, so this only corresponds to the problem that I give you, which is checking whether number is even or odd. Okay, but suppose I give you any other problem. Okay, let it be some problem P, then you can always come up with a set like this, which is the set of strings that are going to be accepted. It may be finite or it may be infinite. Is that fine? Do you agree until this point? Uh, I mean, could you react or something? I'm not sure whether this was clear. Okay. So yeah, so what we are really saying is that if you're given a problem P for which you write an algorithm, there is a correspondence between that program and a language L. So a language L is basically a subset of sigma star. Okay, so that means you can actually think of these two as equivalent notions. So given a language, there is an algorithm associated with it, and given an algorithm, you can always associate a language. Okay, is this okay?
So every algorithm has its language.
Yes. So therefore, if you want to better understand this, you can as well restrict yourselves to studying the languages. Okay, and therefore, when we talk about languages, we need a model. Okay, so generally, when you do coding and everything, the model that you work with, although we don't describe it that way, I mean, it's sort of hidden under the carpet, but the model that we work with is what is called Turing machine, which you'll be introduced to at the end of the course. Okay, but yeah, so that's the underlying model we are working with. So whenever we talk about an algorithm, there's always a machine or a model that is associated with it. Okay, yeah. So yeah, and that's why the one of the fundamental things that we are going to do in this course is to see what kind of languages can be accepted by the model that we are working with, because as you will see later in the course, uh, it's not necessary that every model can uh, accept any language that you want, if that makes sense.
Could I try it? It's like if you give me chance, is explain. Means like the question of that Ahir Rupa, the real
Sure,
world
sure,
use.
sure, sure, yeah, yeah.
I kind of think like languages as functions, and we all know that not all functions are
Sorry, yeah, functions from what is the
means like
domain and what is the codomain?
means like functions in all sense means like function just the function I'm just thinking of like some it is taking an input or giving an output, and there is no specific domain or codomain. Means like there are many functions like which are not computable, right? Only few are computable. It's like if we just randomly assign 0 1 to tossing a coin, then it is like so I kind of think like languages as functions. So not all functions are computable, so we are thinking only some function are computable, so only that have algorithms, right? Which are computable. So I think languages are as functions, uh, and we are thinking of which languages can be computed by the machine. So something like I kind of think we are acceptable. I kind of think in that way, so it helps me apply. So maybe I tried my best. So sorry.
Yeah, yeah, yeah. Yeah, I agree. So does that address your question? I think Ahir. Um,
Yes.
okay, good. Um, yeah, and one more thing is, I think you all must have. I mean, whatever you use PDF or something, Adobe or whatever, right? Any kind of PDF viewer, and you want to look for a certain string, or I mean, even in databases, you want to look for a string of certain kind. You know that maybe uh, it ends with maybe A, and there's some B in the middle, and maybe there is a hyphen somewhere. Okay, so you have a set of rules. You know that this is the kind of string that you are looking for, but I mean, it could have anything in between, right? So all you know is, yeah, all you know about this string is that it ends in A, and maybe it has a hyphen in between, and maybe it has one of the numbers 0, 7, 2 in it, and that is all you know. Okay, but you can't just go ahead and I mean, there are so many strings that could satisfy this property, right? So you can't just go over all of them. So but you can still search this. So what is used here is what is called regex. You might have used this I mean in programming or something. So what you do is you kind of code this in terms of a string. You may use stars somewhere and then write hyphen, and maybe you have a 0 to 7 in between, and then you know that it ends with an A. So what it does is internally it's going to take this string and go and make the search for you. You don't have to explicitly do it all the time. So this regex that is used, which is I mean, you don't care about the implementation when you use it, but this is actually the same as the DFAs that you have seen. Okay, so we'll see this later on. We'll also prove why these are equivalent. But yeah, I mean, I just want to yeah, just give you a connection that I mean, you've used it in some sense, but you only maybe don't know the yeah, don't know this connection. So yeah, Goel, is there a question?
Yes, so is this possible that can I make transition from a state to the other state for multiple symbols in the design of the DFA?
Okay, but that is what you're doing, right? So for 0 you have one transition, and for 1 you have another transition. So
Like say from the state Q naught, I can define a transition that after getting two zeros, 0 followed by a 0, I'll make a transition to the state Q1. And after getting a 0 followed by a 1 over the state Q naught, I'll make a transition say to the state Q5.
hmm. Okay, so if you want that, so for example, you want a transition on 0, 0. Internally, what you're really doing is that you are basically you don't want alphabets here, you want substrings,
Yes.
right?
So can I make transitions over the strings?
So by definition of this DFA, you cannot. It only allows you to read one symbol and then make a transition. I mean, you can define your own model that way, but that whether that model is more powerful than DFA is something that we need to see. Okay, but let's say that you want to make a transition like this. Okay, I mean like this 0, 0. So internally, this is what you're doing.
Yes,
Okay,
yes.
but then we don't know where one goes.
Yes,
So
but then there is a term like say generalized DFA or something similar to that. So what is that? Do we make
um,
transitions for the I mean entire string in that model, or that model is something else entirely
I
different?
think I'm not familiar with this, but I'll look into it. But yeah, but I think as I mean by definition, DFA doesn't allow you to make such transitions because it won't be complete, right? Because then you'll have a state and a symbol for which you don't know where to go.
Right, right. Yes, fine.
Okay, and coming back to your previous question, so Okay, maybe could you reiterate the question so that yeah, and
Yes. So my question was that as far as the models of computation are concerned, so Turing machine is one way of defining computation. Probably lambda calculus, and there are other models which are said to be Turing complete in that sense, and are the other models of computation. And then in the beginning of this session, you said that we can define our own model of computation as well. So now my query is that how to define our own model of computation so that that model is also Turing complete in the sense that whatever Turing machine can do, our model can also do, and vice versa.
hmm. Okay, so okay, so one thing is maybe I'll come to the context of DFAs so that because everybody here may not be familiar with Turing machines, but just to answer how do you define your own models, one thing would be that you can just yeah, just like you said, right, here instead of sigma you want to make it a sigma star. Okay, that would be one different model. Other thing you could think of is um, okay, so here one thing peculiar about the DFAs is that it's a left to right model, in the sense that if I give you a string 101 and you want to run that string over this machine, then q0 on 1 goes to q0. Then you have to read a 0, so you'll read a 0 from here and go to q1, and then you have to read the third letter, which is 1, and then you make a transition. But if I want to process this string over and over again to make some to get some extra information about it, I can't do that with this model because it's a one read one sort of model. You're just going to read it left to right and only once. But then I could, uh, I mean, if you've written algorithms, you would have seen, right? You if given an input, you're going to process it as many times as you want, however you want. So that seems clearly more powerful. So one restriction you could do is okay, instead of letting it read only once, you can make it read twice or something and then ask whether this is more powerful. So this model is also studied. So this is called okay, yeah, by the way, this is not going to come up in the course, but yeah, just to answer the question, yeah, so this model which allows you to read the input twice, like back and forth, is called a 2DFA. Okay, so okay, saying that it reads twice is not exactly correct. It can read it over and over again. So you can go all the way 101 and come back 101 and keep on doing it. Like you can sweep in and sweep back, but you need to read it completely. You can't stop in the middle and go back, sort of. So yeah, so this model is called 2DFA. And now the question is this more powerful? Although we have not defined the notion of more powerful, but okay, maybe this is a good time to introduce that. So yeah, so given this model DFA, we'll ask what all languages can it accept. Okay, and then you ask what all languages can this 2DFA accept. If there is a language which a 2DFA can accept but not the DFA, then you know that 2DFA is more powerful. I mean, if the language is accepted by okay, so if the set of languages accepted by a model, just yeah, just a second, I'll just complete this thought. M1 is a subset of the set of languages accepted by model M2. Then you say that M2 is more powerful than M1. So this is the sense in which we compare two models, and yeah, and it so happens that although this model seems to be more powerful because you have given it extra functionalities, it so happens that this model is as powerful as DFA, in the sense everything that the DFA can accept, 2DFA can accept, and vice versa. Okay, so yeah, so just to summarize what we said so far, the way you can introduce your own models is either add more functionalities to the machinery you have, or allow it to compute some different functionalities, as you will see in this course. So if none of this makes sense, it's okay. You can yeah, you can.
But then this 2 DFA can recognize A raised to the power n, B raised to the power n, I guess, and which is clearly non-regular. You make it a scan for the string and then make a reverse scan, and then you compare the symbols. And so,
Yeah,
yeah,
so note that you cannot write anything. Okay, so it although seems like A to the n, B to the n can be recognized by 2DFA, it actually cannot, because this is a memoryless model. You cannot sort of like map 1B with 1A and keep on scratching off. So if you don't have that power, you can't, yeah, you can check this out. So
yes, yes, I got it. And moreover, I've not seen DFA having multiple number of the tapes. So, like when I said that, can we make a transition for multiple symbols from a state to the other? Probably, I mean to say that instead of scanning, say, making a transition for 00, I mean to say that I would be scanning 0 from the first tape, another 0 from the second tape. So, do we have models, I mean, finite automata models wherein multiple tapes uh, have been studied?
Mm, so one thing is that even in Turing machines, a multi-tape model is same as can be simulated by a single tape model. Those are,
Yes,
yeah,
that
as
is it.
powerful.
Yes.
But I guess that would be the same for DFA, but I'm not sure. But it depends on how the input is given to you. Um, do you mean the input? Because the input is always given on the one tip. That's how we work.
Yes. So, but then the input can be broken down into the chunks, into a block of the size, say, 5. And then instead of using a single tape, I would be using 5 tapes.
Hmm.
And yeah, so slight modification in in the design of the standard
Hmm.
DFA, in case it has been studied earlier. Yeah.
Yeah, I'm not aware of any of such studies, but I would imagine that it may not add to the power. That's my guess, but yeah, I don't have a proof at the moment. Yeah, but you can maybe check it out. Yeah.
All right. Yeah.
Okay. I think Ahir has a question. You have raised your hand.
If we want to search a certain type of string, so we have to make a DFA model for it, so that we can say that we can build our own model, right?
Right. So yeah, what I mean to say is, when you perform such kind of searches internally, you are actually using a DFA, and yeah, maybe in the examples to come, maybe today it's in this tutorial itself, maybe you will see some flavor of regex behind it. Sorry. Yeah.
So
Um,
how we implement DFA to the computer?
yeah. So for that, you'll need some familiarity about Turing machines, which I'm not talking about right now, because that will come up later in the course. So maybe at that point we'll talk about it. Okay, so basically your computers, whatever it can compute in terms of memory and yeah, space and time, that is somehow captured by the Turing machine model. And when we talk about DFS, it only restricts the power of Turing machines in some sense. So Turing machine has a memory, because when I say you have to detect whether a number is even or odd, okay, maybe even odd is a bad example, but let's say you have to check whether a number is prime, then you're going to do some computations on it and remember something. Maybe you'll see whether 2 is a factor, 3 is a factor, and you'll keep on remembering this thing until you reach to a decision whether the number is prime or not. Okay, but let's say I don't allow you that memory. You're not allowed to remember, in some sense. Yeah, then what can that restricted model compute, which is one such model is a DFA. So I mean, so it's basically your computer with some restrictions on it. Um, you might have seen such devices. So, for example, the switchboard that you have, right? Switchboard to a light or something. Okay, so when you switch it on, the light turns on. When you switch it off, the light turns off. There's nothing else that it needs to do. There's no other computation. So that can be thought of as a DFA model.
Okay.
So all the simple machineries that you see around you which don't use much computation, those can be formulated as DFAs. Okay. So yeah, are there any other questions?
What will be the accepting states of A1 intersection A2?
Okay, yeah. So we'll come to that. Okay. I mean, I think in today's tutorial itself we'll come to that. Okay. If not, just remind me in the middle. Okay. And yeah, just to yeah, clarify. So I think we have had some discussions about Turing machine 2 DFA and so on. If that does not make sense, it's okay. I mean, if you're not yet introduced to it, it's totally okay if you don't get it. I don't, yeah, I mean, don't worry about that. But I think, yeah, such discussions may keep coming up in between, but if it doesn't make sense, it's okay to, I mean, yeah. Okay. Yeah, so I'll start with, yeah, maybe let's start with simple questions. Okay, so you're given this DFA and this is the input that's given to you, and you have to tell the sequence of states that it will move through. So if you have answers, you can unmute and tell me or use the chat box.
Hello.
Sorry, did you say something, Gautam?
I think D is the answer.
Okay. Yeah, I'll just wait for a minute, just a minute, for others if they have other answers.
Can I say the answer?
Yeah, sure, yeah.
I think it's C.
Okay. Yeah, anybody who thinks it's other than C or D? Yeah, I see Chintu says B, yeah. Anybody who thinks A or B?
I think it is B.
Okay, yeah, good. So let's go with this input. So yeah, so I mean, you start with the starting state is always the starting state that's given to you, which is Q1. Then you read a 0 from here and you go to Q2. Okay, on reading a 0. Then you read a 1. So from Q2, a 1 takes you to Q3. So you go to Q3 and then, yeah, you read another 1. So Q3 on 1 goes to Q6. So you are at Q6. Then you read a 0. So Q6 on 0 makes you stay at Q6. Then you read a 1. 1 takes you to Q2. Sorry, 0 1 1 0 1. sorry, am I, yeah, there's one more, yeah, 0, you go to q5 and then you read a 1, so q5 on 1 stays at q5. So is this fine? Yeah, good. So are there any questions? Anybody? I'll just wait for maybe a few seconds.
Ma'am, can you tell how can we minimize this kind of DFA?
Yeah, so we'll come to that maybe by the end of this tutorial, or if not, then maybe next week, because just today I just want to cover the notion of closure properties and so on. But yeah, we'll definitely come to it maybe by next week. Is that okay?
Okay, ma'am. Thank you.
I hope this is fine, right? So those of you who had answers other than B, I hope this clarifies. Okay. So yeah, so here's another DFA, and like I think one of you answered, we say that a string is accepted by the automaton if it reaches one of the final states. So here these are the final states that you have, q2, q4 and q5. So you need to tell which one of these strings is not accepted. Maybe there are multiple answers, so take your time.
Option C.
Okay, yeah, let's wait maybe just one more minute for others to solve. Okay.
Ma'am, I think answer is A, B, and D.
Yeah, I think you're answering the complement of this question. So you want to find out what is not accepted. So uh, yeah, I mean, okay, yeah, let's go over it. So yeah, I think most of you answered it correctly. So the answer is C. So if you run, let's just run this one more time. So let's say the input is 0, 0, 1. Then from Q1 on 0, you go to Q2. 0 from there takes you to Q3, and a 1 from there takes you to Q4. Q4 is a final state, so this string is accepted. Then you look at 1, 1, 0. So Q1 on 1 stays at 1. Another one also stays at 1. Then you read a 0. That takes you to Q2, which is a final state. So this is also accepted. But if you read a 0, 0, from Q1 you go to Q2. From Q2 you go to Q3, which is not a final state. So therefore this string will be rejected. Okay. And yeah, I'll not do this last one, but I guess you can verify that this will also end up in a final state. So the answer is C, as most of you correctly answered. Yeah. Yeah, I think what you were answering, Anubhav, is probably which are accepted, which was ABD. Okay, so is this fine? Um, okay, so I'll move on to the next question. Yeah, so this is the automaton that is given to you. And just to clarify this notation, for example, this is, yeah. So what we mean is W1 is any possible string over 0, 1, and W2 is any possible string over 0, 1. Okay, so this will be the set of all the strings with 0, 0, 1 in middle, and they could be preceded and succeeded by any possible string. So that is what this set means. Similarly, you can read all the other sets. So the question is, which of these is the language that is accepted by this automaton? Yeah, if there's anything that is not clear, you can ask me.
Ma'am, I think answer A.
Yeah. So yeah, those of you who answered A, what is your reasoning behind it? Yeah, any one of you. Yeah.
I think we are accepting the states which are actually kind of middle between 0, 0 and 1, and whatever is behind and whatever is before, after, sorry, these are not kind of, we are not taking account.
Hmm. Yeah. So yeah. So there is, I mean, in this case, the automaton that's given to you is small. So by small, I mean the number of states here is just 4. So I mean, if you do some sort of a trial run, you'll get an idea of what this um, automaton is is accepting and what it is rejecting. So okay, so for example, you can even eliminate the rest of the options. So for example, let's look at this set. Okay, in particular 10101 is one of the elements of this set, and so on. There are infinitely many. If you try to run this, it will end up rejecting this string, and in all the three cases you will find some string in this set which the automaton will not accept. So then clearly these cannot be the languages. Okay, and I think Anubhav and yeah, maybe others of you observed, if you look at what this automaton is doing, it's actually looking for this substring 001. Maybe there's something before it, and maybe after reading 001, maybe it says any number of zeros or any number of ones. That's what this W2 is. Okay, so that is the pattern that it's doing. But the point is that I've still not formally proved it. So all I'm saying is, if you want an answer to this, you could run these some elements here, and you'll see that those are not accepted. Okay, but there is a formal way to show that this is precisely the language. So L is equal to W1001 Okay, to show that this is precisely the language of this M. And we'll see maybe in the next week, or in a week or two, we'll see how to do that. And the reason we need this is because if I give you a very large automaton, maybe it has 1,000 states or 1,000,000 states, then it will be very difficult for you to manually go over it and see what kind of strings it is accepting and what sort of behavior is happening. Therefore, you need a formal method, sort of a mechanical way in which you can find out the language exactly, no matter how complicated the automaton is. So, that is something that will come up later. But yeah, I mean, you don't need that for this example. Okay, so is this okay with everyone that this is, I mean, this is the correct answer?
And what that method is?
So I think you would have seen. I don't know whether DFA minimization will give you that, or even converting it to regex. That would directly give you the language, right?
Yes, yes, yes.
Okay. So, okay. So we'll see that later in the course. So, but I mean, if there's any other doubt, then let me know right now. Okay, good. So we'll move on to the next question. Yeah. So L is the language which consists of strings that end with 101. So is the, yeah, when do you say that a language is regular? This is just a definition that you need to remember. You say that L is regular if there is a DFA um, M such that language of M is equal to L. By language of M, we mean all the strings that are accepted by M. Okay. So basically, the question is whether you can come up with a DFA for this language. Okay, so those of you who said yes, can you tell me one DFA, one construction for this? I'll just draw, you tell me the states. I mean the transitions.
So after getting a 1, make a move to the next state, say Q1. Uh, and after getting a 0, make a move to the state, say Q2. Uh, say, oh, I see. Yes, yes, 1 and then 0. And then after getting another one, I did not thought it that way. 1 and then make a move to the final state. But then we'll have to look for the possibilities over each of the intermediate state as well. So yeah, but then so what if I get a 1 and then 0 and then 1?
Yeah, just a
So
second,
now,
just hold on 1 second. So does everybody see why this is not like the final answer? What is the problem with this?
We need to backtrack the inputs of 0 to the starting
Yeah,
state.
correct. And by definition, this is not a DFA also, because by definition, from every state, you need transition on every alphabet. So here, sorry, from Q0, you only have defined a transition on 1. We don't know what it will do on 0, and so on. Like similar problem for all the states. Yeah. Okay. Yeah. So yeah, who would, yeah. Hmm.
so after getting now we explore the possibility over the state say Q1. So what if I get a 1 over the state Q1? So I will prefer to keep on moving to the state Q1 only,
Correct.
because
Yeah.
I'm looking for the acceptance of 101. Next, over the state Q2, I know where to move after getting a 1, but if I get a 0 here, And since I want to accept 101, so now if I get a 0 here, this will become 001, right? So after getting a 0, probably I'll have to repeat the entire logic from the scratch. So I'll make a move to the state, say Q naught. Then,
So from Q2, you want to go back to 0.
yeah, because I have scanned 1 0, and if I get another 0 here, yes. And after reaching to the state, say Q3, if something is remaining, is still remaining in the string, I'll have to look, say, what if I get strings are ending with 101. So, what if I get a 0 over the state Q3? So, if I get a 0 over the state Q3, that will be same as repeating the entire logic from the scratch. And probably for 1 as well. So, Q3 to Q naught, I'll make transition for either for a 0 or for a 1. And then one transition is remaining for Q naught. So, I'll keep on moving to the Q naught only.
Okay, so Q3 on 0, where do you want to go?
So for Q3, since I want to accept 101 and 1 is has been scanned, and then I would like 101. So 1 has been scanned. So I will make a move from Q3 to Q1 in the hope that probably I will get 1 0. No, 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 no.
Yeah,
1
yeah,
0.
yeah, that is.
Not right,
No,
not
so
right.
you have seen. Okay, let me just. I think your logic is correct. So let me just explain the Q2 thing first, and then we'll look for the remaining transition. So what he's saying is that, let's say you are at Q2. Sorry, yeah. Let's say you are at Q2. Then what that means is you have already seen a 1, and you have already seen a 0. Okay, so you have read something earlier and you have seen a 1 and a 0. What you want ideally is a 1, but that didn't happen. You instead saw a 0. That is as good as you're going to look for. You're going to look for if the remaining substring has a 101 somewhere. So it's as good as starting back from the beginning. So you'll search for it starting from Q0. Now let's see what happens at Q3. Okay, so if you are at Q3, that means you have already seen a 101. So you read something earlier and you have already seen 101. Okay, but yeah, but what could happen is maybe you saw a 0 after this, because you want to end with a 101 rather than have it somewhere in between. Then you don't go back and start from beginning, because if you think of this part, you have already read a 10 and you are waiting for a 1 here. So which state remembers that you have seen a 10? It is Q2, because if you see a 10, you come to Q2. So you'll make a transition from Q3 to Q2 on 0. So you can think of it this way, that at Q0 you are yet to see anything. At Q1 you have seen 1, at Q2 you have seen 10, and at Q3 you have seen 101. Okay, so yeah, so therefore when you see this 10, you are actually going to go back to Q2, because Q2 is the state that remembers that you have seen a 10. So if that makes sense, can you complete this Q0? It doesn't have a transition on 0.
Yes, so for 0, if it starts from 0, then I'll keep on moving to the state Q naught only.
Correct. Yeah. So you will stay at Q0 because, yeah.
One transition is remaining for 1 over the state Q3. And in that case, there would be, if I get I see 101, and then after 101, if I get another 1. So then that would be the beginning. I mean, the entire logic should, if I get, say, 101 and then another 1, that is of no use. Then I'll make a move from the state Q3 to Q naught.
No, but this one could be the beginning of some 101.
So in that sense, yeah. So from Q3 to Q1, then yes, right.
Yeah. So you'll go from Q3 to Q1 on a 1. So does this make sense to everyone? The way we ended up adding all the arrows If not, then yeah, please ask, I'll repeat. Okay, okay, good. So yeah, I think we'll move on to the next question.
I have a question.
Hmm.
If we can't go back to the string, then how we can go back to from state Q3 to Q1 and all this?
So what we mean by going back to the string back then in that context is that if let's say 1011, this is the string. What we mean by that is if you have read 1011, and let's say 10, then you can't go back and read this. This is what we meant, but that is not what we are doing here. So if you have to run any string, I mean any 01 string, the way the machine works is that the machine will only keep, I mean, let's say on 10110, it on 1 it says this, on 0 it goes here, then 1 and 0. Okay, it is not, the machine is actually not making the input run back again in its computation. It will only read it once.
It has a memory, so
Yeah, but I mean, uh, this machine during its computation is not really reading any input again, right? Any part of the input is not being read more than once.
yeah, I got that.
Yeah, but yeah, you're right. So these states are actually memory. I mean, but the reason why we call it sort of a memoryless model is because when you are at a state Q1, okay, you basically don't know what happened earlier other than the fact that you are here. That's what we mean when we say it's memoryless. Okay, it only remembers that I am at Q1, and if I see a 0 further, I'll go here. If I see a 1 here, I mean, it will just follow the transitions, but it doesn't remember the history of what the string was.
So it remembers, Q1 remembers 1 and Q2 remembers 1, 0.
By 10, what do you mean? The input or the transition?
The input.
Mm, well, no, I mean, okay, I mean, what we mean is it doesn't remember the history of, I mean, of what, I mean, it doesn't know. If you are at Q1, you don't know what you read earlier. What was the string before it? It could have been anything, anything which follows some property. I mean, that's all we mean. Um, yeah, so when I wrote this 1 and this 10, all I mean is that this is the property that we want Q1 to have. That I want to land in Q1 when I have something, and I want to land in Q2 when I have something.
Okay.
Okay, but I mean, you see, right, that I mean, Q1 by itself will not remember what the previous string was that you read. As in, it could have been a 01, it could have been a 001, 0001, or anything that Q1 doesn't know.
But Q1 will
Yes.
definitely,
Yeah, go ahead.
but then Q1 would definitely be knowing that it is one distance away from the initial state. I mean, even though the finite automata does not have memory element, but still the memory, I mean, the number of the states is equivalent. I mean, the memory in the finite automata in a way would be equal to the number of the states in the design.
Yeah, that
So,
is correct. Yeah, yeah.
so at least this Q2, I mean, while designing this finite automata, we also took the help of this fact that if you want to scan, say, another one, then this much portion has already been scanned. So in
Yeah.
that sense, yeah, Q1 probably all the states might be knowing that how far they are from the initial state.
So that is not well defined, because how do you define distance? Because if um, I mean, if I follow, let's say, 1 1 0, uh, yeah, if I, let's say, follow 1 0, then I go to Q2 from Q0, but I could have as well, I mean, okay, I don't know if I have that many paths here. Let me just yeah, let me take q0 and q3 as example. Okay, so we are looking for a distance notion here. So one way that you could go from q0 to q3 is by following this path. The other way is that you go from q0 to q1, maybe read a few zeros here, go to q2, go back to q0, and then, like, yeah, I mean, stay here for longer until you finally go to q3. Or, I mean, in this case, it's very linear, but what I mean to say is there could be several other paths that take you from Q0 to Q3, and they may have different um, lengths.
Minimum path, the path of the minimum length.
Um,
Like say, can we think of
okay, sure, yeah, let's say it's a path of minimum length. Yeah,
something
then,
something in terms of the prefix kind of the thing. Like say, what would be accepted beyond Q2? So whatever is being accepted beyond Q2 must have 10 as a prefix,
hmm,
and then followed by anything. That sort of thing.
hmm.
So that much memory is there in the Pirate automata, I think.
Yeah, yeah, I mean, in fact, yeah, all the states have some intrinsic memory. Therefore, the number of states here corresponds to the memory that you have used. But when we say it's memoryless, it's in the sense that the state by itself doesn't know the history, like, about the previous, or you can say that it's a unit memory. That's what.
Yes, right, true. Yeah.
Okay. So, yeah, are there any questions? Other questions? Yeah. Okay. Then, yeah, we'll move on to the next question. So, yeah. So let's yeah. So given a DFA, you have seen maybe a few examples by now of how to um, check whether a string is accepted, or find the language that is accepted by it. This is a reverse question. You have been given this language, and you want to come up with a DFA. I think we did one example a couple of minutes ago. So we'll maybe do a few of these. So let's say A, you want to come up with a DFA that accepts all strings with even number of zeros, and the alphabet is 0 1. So yeah, when you have your answer, one of you can tell me. I'll draw it here. Yeah, Arijit,
Could
you.
I,
Yeah.
means like could I try first? Or
Sure. Yeah.
so let I say means like because the first one is even number of zeros, right? All strings. So So we only care about zeros. It's like one has nothing to do with the count, right?
Correct. Yeah.
So so let us assume is like two states. One state, let's say Q naught for even number of zeros, and another is Q1 for odd number of zeros.
Yeah.
Uh,
Okay. So I'll just write
so
down. Yeah. 1 second. So this is even zeros. This is what the state is. Okay.
so from even, if we get a zero, if we are already at even state, and if we get a zero, so we will move to odd state, right?
Okay. Hmm.
And if we had one, and if we had even state, and so we will move to even state, and vice versa for odd state.
Okay.
Get me? So something like, so accepting state is even state. So something like two state.
Yeah.
Can you get me? And the similar thing for odd number of zeros.
Yeah.
The second one.
Yeah. Correct. So, um, yeah. So I'll just repeat whatever you said. So what he's suggesting is that we have two states. This one remembers that we have seen even number of zeros so far, and this one remembers that we have seen odd number of zeros so far. So from here, if you see a 0, that means now the number of zeros is odd because you had even earlier, and now you see one more, so you should go to odd state. But from odd, if you see one more 0, that means now you have even number of zeros, so therefore you should go back to even. And ones are not really taking part in this, so sort of oblivious to what it does. I mean, so you just stay on the same state wherever you were if you see a 1, and you want to accept if the number of zeros is even, therefore you make this a final state. And same logic applies to B, only that you'll make odd as a final state and make even as a non-final state. So yeah, is this okay with everyone?
I have a doubt,
Yeah.
but how will the state know that the previous inputs were even or not? Wasn't the question itself was to define how to get to the even number of zeros?
Are you asking how do we know whether this is odd and whether this is even, or are you asking whether how do we make transitions?
No, no, I'm asking the first case. How does the state itself knows that the previous inputs were even or not?
Yeah, so I mean, basically, you can think of this as Q0 and think of this as Q1. What we're saying is that we are going to define the state in such a way that you will always end up here if you have seen even number of states, and therefore we are going to add transitions accordingly. Okay, so like for example, I want the state to be reached only if you have seen even number of zeros. So whenever you see a 0, that means it's violated, so I should go somewhere else.
No, that's what I'm asking. What would be the defining criteria of getting to that even state? Like, what would be the steps before that state to get to the even? Like,
Okay, so I'm not sure if I understood your question clearly, but initially, when you have not started reading the string, okay, then you have not read any 0. Okay, so the number of zeros you have read is 0, which is even. That's how we define it. Therefore, you always start here. I mean, at the beginning, when you have not even read anything and you are at the start state, then the number of zeros you have read is even.
yeah, okay, I got it.
Okay, good. Any other questions?
Can we make four kind of states even odd, and we can replace this with Q after whatever it is?
Yeah, correct. So, you have any other automaton in mind? Yeah, maybe can you describe the automaton if you have one?
No, ma'am, currently not. But yesterday, what I am studies was we can make four kind of even, odd, even, and odd, and then
Sure.
we can move states.
Yeah, I think that one probably remembers the ones as well. But yeah, that may be redundant. So you can have different, like for the same language, you can come up with different, many automatons. But then that brings up to the question one of you asked earlier, which is um, how do you know? I mean, if I want to compare two automatons, I would ideally want the one which is smallest in the number of states. So that brings up to the notion of DFA minimization, which we will see later in the course, maybe next week, which is that if you have a larger automaton, you can always shrink it down and bring it to the minimum number of states possible. There is an algorithm for doing that, which you will see. Yeah.
So can I drop it?
I have a question out of curiosity. So, is there a mechanism to minimize Turing machine as well, similar to the finite automata? That for every Turing machine, I can find a minimum Turing machine.
Hmm. Okay, yeah. So you can think of the Turing machines in this similar. I mean, sorry, in this similar representation where the state you have states, but the only thing that will change is that you'll have some kind of a memory. So if your current input is this, current state is this, and the current um, yeah, then where do you go, left, right, and so on, right? So what will happen if you apply the same algorithm? Hmm.
Because then showing the equivalence of two programs is undecidable, I guess. And program and Turing machine are interchangeable. So
Yeah.
if I have a procedure to minimize the Turing machine as well, probably I'll have to show that whether two
Hmm.
programs are doing the same thing or not.
Hmm.
Since that is
Yeah.
not possible, so such a
So
mechanism which you mentioned for the finite automata
hmm.
may not be possible for the
should
higher
not
models.
yeah, should not exist. And yeah, the same procedure that we have yeah, so the procedure that we have for this will fail at this point, probably, that we have this left and right thing, right? So that may not be replicable in that same algorithm as it is. I'm not sure, but yeah, that's a good question. Hmm. Okay. Yeah. So are there any other questions before we move to C? Okay. So anybody, if you have worked out the answer for C, would you like to share? Even if you have like partial thoughts, we can work it out on the way, on the fly. So feel free to share.
Mm, I don't know, but let me try.
Yeah, yeah,
Okay,
sure.
like okay, it is saying means like it is basically number of zeros are multiple of three. Okay, so uh, uh, let's start with a state Q naught. So it's like if we
Yeah,
get a
just
zero,
one minute.
if we get zero, we will move to Q1. So and if we again get a zero, we will move to Q2. But and basically and if I again get a zero, I will move to Q naught.
You'll move to
Uh,
Q naught. Okay, sure.
okay, yeah, basically what I'm doing is because what I have created three states because only remainder can be 0, 1, 2, right?
Correct. Yeah.
So and if and if there is one, we do nothing. So we remain in the same state. So so basically acceptance state is Q naught. So uh, so I'm thinking like I'm not sure if it is correct, but maybe I'm thinking like that. Uh,
Yeah,
This is
Hmm.
correct.
Goel, yeah, sorry.
Yeah, I said this is correct. Yeah.
Yeah, yeah. Yeah, so yeah, this is the logic is also perfect. So you're saying that Q0, remember, I mean, you want to come to Q0 if you have seen zero number of, I mean, if the number modulo 3 is 0, and to Q1 if the residue, if you divide the number by 3 and you are left with the remainder 1, you want to come at Q1, and if you are left with the remainder 2 on division by 3, then you want to come to Q2. So that is precisely what we are doing here, and we are just ignoring the ones. And like yeah, sorry, I forgot. Someone asked earlier, why do we start at Q0? Because at the beginning you have not seen any zeros, therefore the number of zeros modulo 3 is still 0, therefore you want to start here. Okay, good. So any questions about this?
So whenever null is the part of the language, then initial state would also be same as the final state.
Yeah, yeah, when you have not read anything, yeah. But epsilon is not, an empty string is not, we are not reading an empty string, that's what I, right? I mean, epsilon moves are not allowed here.
Yes, yes. Epsilon moves are not allowed in the DFA. I mean to say if null, I mean nothing.
Correct,
Probably how
yeah,
to
yeah,
this
sure,
is.
yeah, empty string sort of, yeah.
Yes.
Mm, yeah, yeah, sure. Okay, so maybe we won't do D for now. You can try this out, okay? And yeah, I think I forgot to say this in the beginning. All these sessions are recorded, and a link will be shared so that you can view it whenever you want. Also, all these notes will be uploaded in the drive. Yeah, I think the link and all will get shared to you. I'm not sure if it's already shared, but yeah. So you can try this out. So there may be some questions that we leave out, and you can try it out. If you need any help with it, then maybe you can ask in the next tutorial, and if there's time we can discuss that. Okay, so this one maybe you can try. Yeah, so okay, maybe seventh one also you can try out, because we have seen questions of this flavor. Yeah, Namya, yes.
In the previous question that we discussed,
Okay, yeah.
would the DFA diagram be any different if the equal to sign was not there in n greater than 0?
mm,
Like if the null strings wouldn't be considered.
okay, so okay. So you want at least 1 0 to be there, um, at least 1 0, and you want it to be a multiple of 3, right?
Yes.
Yeah, then you need to modify it slightly. So can any one of you think about the modification? Yeah, and yeah, great question. Yeah. So you want,
So I'll add a new initial state, and then from the new initial state, I will make a transition corresponding to a zero, and then the entire this stuff can be repeated then. Just to include this fact that everything should start with, I mean,
Okay, so you
instead
introduce.
of 1 0.
Yeah, so let's say Q star is the new initial state. I'll use a different color. Then where do you go?
So from the Q star, after getting a zero, make a move to the state Q naught. Yes. And now we can have, but then what was the question? That should have at least 1 0, and then, oh, I see. Yeah.
Hmm.
The question was different. No, this will make the entire design incorrect.
Yeah. So any other thoughts? And anyone? Yeah.
So what if we add another final state?
Okay. So
The,
and I'll.
uh,
Huh. Okay.
so instead of backtracking the Q2 to Q0, we'll add another state Q3 and make it a final.
And sort of simulate the same logic. So yeah, that you'll need more states. You can't do with three. So what uh, she's saying is you sort of use an extra memory. Okay. Um, okay. At this point, I know that I have read three zeros and at least 1 0. So I should accept this. Okay. And now what you can do is repeat this same logic, thinking of Q3 as your new state. That is, from Q3 if you see a 0, go to Q4. From Q4 if you see a 0, go to Q5 and back. So this is exactly what we were doing here, same, but this part, make sure that you have seen at least 1 0.
Yeah, okay, got it.
Good. Okay. Yeah, any other questions, anybody? Yeah, maybe just to note, maybe you don't need to Q4, Q5, maybe you could reuse these states. I mean, you can maybe optimize this, but yeah, this is one construction that will work. Okay, good. So yeah, let's come back to this question. So you have you have these three statements and you want to find out which of these are correct. Multiple answers may be, yeah, true. By multiple answers, I mean multiple statements may be correct. Yeah, maybe I'll just wait for a couple of seconds. I think there are two answers so far. One is D and the other is C. Okay, so let's first look at the statements 2 and 3. Those are the least controversial. So this says that DFAs can have multiple final states. That's something we have seen already. There could be, in fact, multiple final states. And this says that if you have a DFA M for language L, then you can obtain a DFA M prime such that language of M prime is complement of L. That is, set of all strings that are not in L. So M prime should accept all the strings that are rejected by L, and it should reject all the strings that are accepted by L. So this is something we saw earlier by an example. Here A and B are complements of each other as languages, and if you switch non-final states to final states and final states to non-final states, then you get the machine for the complement language. So the proof of this can be formally proved, although I'll not do that. But yeah, if you have some idea about proof writing, then try this out. It's a maybe 3-4 step argument. Okay, so 3 is also correct. And what this says is that if L is regular, then L complement is also regular. So therefore languages accepted by DFAs or regular languages are closed under complementation. So this is the kind of statement that you will these kinds of statements you'll come across this often throughout the course. So yeah, that's it. And about statement 1, okay, by definition we said that okay, let me go back all the way. Yeah, by definition we said that there's only one initial state. Okay, so therefore by definition you cannot have more than one initial states. Therefore yeah, therefore statement 1 is not correct. So the correct answer is C. And to address Goel's point, so what he's saying is that let's say you have multiple start states, then you could make some kind of a move to merge them together somehow and get to a single start state that will give you an equivalent DFA for the same language, sure, but by definition this model with several start states is not called a DFA. That's what we mean. Is this okay?
Yes, that's fine. But if I include two epsilon moves, a multiple number of the epsilon moves to create a new initial state, and then we have the procedure to, because this inclusion, I mean including epsilon moves will make the entire thing non-deterministic. So
Correct.
then I can convert that in DFA into the
Yeah, sure,
DFA,
sure.
and yeah, that sense.
Yeah, you can get back a new DFA which accepts the same language, but all we are saying is that by definition, if I give you a diagram of a DFA with several states marked as initial state, then that model is not something we'll call a DFA. That's all.
Yes,
But
I don't
yeah,
exactly remember, but then there used to be a term transition graph, I guess. In the
transition table.
transition cable is the representation of the finite automata.
Yeah,
However, there used to be another term, transition graph, and there the multiple number of the initial states were allowed, but I don't remember for what purpose they were including the multiple number of the initial
do you mean
states.
configuration graph or something?
Transition graph used to be. I remember this used to be the standard term. Transition graph. Earlier, the people used to study the transition graphs first, and then move to the finite automata. In many of the textbooks, still this term is being used, but I vaguely remember. But then in that transition graph, multiple initial states were allowed.
I see. Okay.
Yes, yes, yeah,
Okay. Yeah, I'm not aware of this term. Yeah.
yeah.
Okay. Okay. Good. So yeah, I think it's 8:36. Maybe we can do. Um. Yeah, maybe this one I'll leave out so that you can take your time and try this out. you'll be able to do this. And yeah, maybe let's just do let's see whether we can do two questions or one. But yeah, let's say yeah. So the question is that you have this currency denominations of 1, 2, 5 and 10 and 10 rupees. And I mean, we don't worry about the finiteness of it. You have as many ones as you want, you have as many twos and so on. So let's say those are infinitely many that are available to you. Okay, but you want to come up with a sum of 10. So they'll give you in any order, maybe 5 and 5, or maybe 5, 2, 2 and 1, and so on. It could be any combination, but they should all add up to 10. So you want to come up with a DFA which will implement this design, in the sense that you want to accept only if the sum is 10. Okay, so yeah, if the question is clear, just take some time and yeah, let me know one such construction of a DFA. I hope the question is clear. If not, I mean, I can repeat. Otherwise, if you have partial ideas also, it's fine. We can build it up together. But yeah, just share your thoughts.
Currently the parish. Okay, sorry.
Sure, yeah.
Correct. Yeah, it's like I have not done fully. I'm just
Yeah,
saying.
that's fine. Yeah.
Okay, I'm thinking of states 11 means like if the money collected is zero, one state, one collected is Q1, 11 states like that.
Okay, sure. Okay, I'm sorry. Yeah.
Uh,
So,
so and if, uh,
okay, I'll just not draw. Maybe I'll draw as and when we need it. Okay.
so I'm thinking because I'm thinking 11 state uh, uh, because the fare ticket is 10 rupees and we must track the running total, right? Because the uh, if the 10 rupees is reached, we print the ticket, and if it is greater than 10, if the extra money that is like 13, 14 is not accounted. 1, 2, 3, that is 3, 4 is not accounted.
Okay, yeah,
So
sure. So just to make the question simple, let's say we are at the moment. Let's not worry about the passenger giving more than 10 rupees. Okay, let's say you are given at most 10 rupees, then maybe we can modify it to greater than 10 or something. So it just makes it easier to do with less than equal to 10. So yeah.
okay, let me think about it. So just
Yeah, and okay, just to yeah, make things clear. So what is the sigma here? What is the alphabet?
Here,
1 to 5, 10.
Correct.
yes,
1 to 5, 10. And to answer one of the questions in the chat, yeah, so I think yeah, this will need at least 10 states. And to prove that is something you'll learn how to do that in the next week when we talk about DFA minimization and so on. Yeah, otherwise don't worry about it. If the DFA is large, it's fine for us as long as it's correct. Yeah. So yeah, so I think I'll just build up on what you said. Okay, so what I'll do is I think, yeah, let's say we have the states q1 to q11. I'm just renaming those. So let's say this state, you want to come to this first state if the sum that you have is 0. Initially the sum is 0, and then let's say you have 11 such states. Depends. So you reach 1 when the sum is 1, you reach 2 when the sum is 2, and so on. Sorry, I think this should be 10. Okay, and you want to accept when it is 10, so 10 is your final state. Now can you think of some simple transitions directly from 0?
zero. If we get one, so we move to Q1. If we get two, we move to Q2. If I do that.
Correct. If you see a read 5, then you go to Q5, and if you see a 10, you go back to 10 and you accept. Okay, then what do we do? So all the transitions for 0 are complete. We have transitions on all 4 alphabets. From 1, how do we add the transitions?
Similarly, means like if we get a 1, Q2, 2, Q3, 5, Q6.
It will end up at 9.
And if at 1 we get 10, so it will be invalid, as you have said. It's like, or
Okay, so are you saying this, that we keep on adding like this? Is this what you're saying?
yeah.
Yeah, so you keep on doing this from 9, if you see a 1, you go to 10.
Or maybe we could. Okay, but maybe we could do like that also mean like from Q1, if we get a 1, we move to Q2.
By Q1 you
If
mean 0.
it's like Q1 means like 1. I was drawing for 1.
Okay.
Okay. If I get a 1, I move to 2. If I get a 2, if I have 2 alphabet, so I move to 3.
3, correct.
Uh,
Yeah.
so
If you see a 2, then the sum that you have so far is 3. If you see a 5, then the sum becomes 6. So
yes. The only problem here is if I get a 10, then it is become invalid. So how?
correct.
9 will be the accepting state for that.
So 9 only represents that the sum you have so far is 9. So you only want to accept if it's exactly 10. So from 9, if you get one more 1 rupee, then you should go to 10 and accept.
Yes.
Okay, and yeah, so similarly you can basically add transitions from if you are at state Q and you see the alphabet, let's say R, then you should go from Q to Q plus R. That's the way we defined it. Right. Now the question is, what do we do if the sum is exceeding 10? Okay, so let's say I want to reject. Okay, let's say I want to reject if the sum exceeds 10. So from 1, if I see 10, then my sum becomes 11. So what I'll do is I'll introduce this new state. Let me call it 12, and this is a rejecting state. Okay, you'll just reject it. That's a convention that I want to follow. Similarly, from 9, if you see anything, if you see 2 or 3 or 5, you will go to 12 and reject. So similarly, like draw these arrows. So 12 is like a dead state for us. Okay, and yeah, this is not the way it is written. I'm just shortcutting for now, but you should ideally always add arrows. I'm just shortcutting for now. Is this okay? Okay, good. Um, so we'll just move on to the next question. Now, I'm not sure if we'll have time to finish it. But yeah, let's see. Okay, so A is the language, which is a collection of all the strings that begin and end with the substring 0, 1, 0, 1, 0. So for instance, this string itself is an A because it begins with 0, 1, 0, 1, 0 and it ends with the same string. Similarly, if this is also a part of the set A because it starts with this and it ends with this, and so on. You can come up with infinitely many examples, but these are just a few examples of. And B is the set of all strings which begin and end with the substring 1, 0, 1, 0, 1, 0. The question is, what does this language A union B represent in terms of words in English? That's all.
It's like either A is present or either B is present. Just
Yeah.
like either substring A is present or either substring B.
Yeah, just present is not enough.
Maybe
Because
they any string should start with either 0 1 0 1 0, which is A, or end with 1 0 1 0 1 0. I think so.
yeah, right. But for example, this particular string, yeah. So will this string be in A union B?
I think so because it is in A.
Are you sure is this a name? Because A says that it should start and end with 0 1 0 1 0. It starts with 0 1 0 1 0, but it doesn't end in that.
Okay, yeah,
Right.
sorry.
So it's not in A, it's also not in B, because although it ends in 1 0 1 0 1, it doesn't start with that. So this string will not be in A union B. And does everyone agree? Yeah, go ahead.
So, what's the meaning that it is ending with this 0 1 0 1 0? Because I think that this is ending with 0 1 0 1 0. Oh, you wrote one extra one. So
Yeah.
if I only consider 0 1 0 1 0,
Hmm.
then this is starting as well as
As well
ending
as
with.
ending. Yeah.
Oh, yes. Okay.
Yeah, so can you now express what does A union B contain exactly, just in English?
They both conditions should be met.
Hmm.
So it's like
Both as in
Either of.
correct. Yeah.
yeah.
So yeah, if it starts in 1 0 1 0 1 0, then it should also end in 1 0 1 0 1 0. If it begins with this, then it should end in this. But one condition here and one condition here, that won't work. That's all. So basically, it's the set of strings that, let me call this W1, this is W2, that Okay. So, so yeah, so the question is, let's say you have a DFA for A and you have a DFA for B, which you have because we know that these languages are regular. So can you use A and B directly to come up with the DFA for A union B? Maybe just to make things easier, let's replace 010 with a shorter string, uh, 01010 with this, and replace the other with this, just so that it doesn't get very clumsy. Okay, so yeah, have you done something called product construction in the course yet? Yeah, anybody?
So product automata can be made, and synergistically we can, we can use that process by creating by taking the Cartesian product of the states of both the machines too. But then this such a method, product automata, does this work for higher models also, or only for
By
lower
higher
stuff?
models, you mean PDAs and so on. Uh,
Because there we consider the union and these set theoretic operations at the level of the language, not at the level of machines, I guess.
yeah, but the thing is, for example, in terms of regular languages, we know that it's closed under union as well as intersection and complement and so on. So you can apply this product construction for intersection. But when it comes to PDAs, grammars, those are not closed under intersection. So even if you have a grammar for A and a grammar for B, you can't use such a construction to get a grammar for or a PDA for A intersection B.
Yes, and
But
this
yeah, DFAs, sorry, but yeah, Turing machines are closed under intersection as well. So you can actually do something similar to product construction there.
yes. But then how difficult it is, this is slightly related question, but then how difficult it is to write the formal proofs in theory of this in this subject, because in one of the video the professor said that the proofs are not that difficult, and then whatever you say in English, you simply translate that using the mathematical notations. So, but then how really, difficult proof writing is in this subject?
Hmm. Okay. So okay. So at least until we are DFAs, okay, everything it's more like a template. So whatever we are the theory that we are developing for DFAs, we will be asking similar questions for the models that are to come. So if you get familiar like with DFS, it will be easier and easier to extend those ideas and proofs to the more and more stronger models. And at least in this course, the proof writing wouldn't be very difficult because it will follow a template. So when you are showing that something is not regular, which you will see maybe next week, pumping lemma and so on, there is a template that's given. I mean that's fixed. So if you have to show it's not regular, then you will demonstrate one string and so on. So if you know, I mean, it just takes a bit of practice. Once you have that, I mean, in memory and in understanding, it's not difficult. I mean, you don't have to create something new, you just have to apply it. So it will be mostly like that. So proof writing, you just need to maybe like see a couple of examples and it should be fine. Won't be anything tricky.
Okay, all right, fine, thanks.
Okay, good. So yeah, so coming back to this product construction, um, yeah, maybe I don't have enough time for that, but are there any questions about product construction in the assignment or something? I mean, is it critical for this week, or we can push it to the next week?
So I have a query. Like say in the product construction, we can show the regular language is closed under union intersection, and then set theoretic minus. And what other operations we can show by using this product automata?
Hmm. Okay, so yeah, it should be some function of the final states in the first order in A and the final states in B. I think as long as that function um, is well defined, I think any operation that we define should be doable, right?
Yes, yes. And moreover, this method is applicable only for the DFAs, not for the NFA thing.
Yeah, that is correct. Yeah.
Yes, yes.
But yeah, again, we'll come to, yeah, we'll visit this again when we come to NFAs, I think. Yeah. But um yeah, I think this will take some more time to define. So is this okay if we talk about it later? I mean, the next week.
Yes, sure. And in which week would you be discussing Chomsky classification?
Okay. So I'm not sure about the order in which the content is coming, but my guess would be week 3 or something. It should be 3. At most 4, not more than that. Yeah.
Yes. Oh, I guess.
I
And
think yeah, 3, because you'll be doing NFAs in week 2, and then you should be starting with grammar. Yeah.
because as such, probably the Chomsky classification is not uh, given uh, in the lectures
I see.
as such.
Oh,
So
okay.
that is why I asked this query. Yeah.
Oh, okay. Okay. In that case, maybe, yeah, maybe whenever we have covered enough material, and we have time, then we can maybe introduce and have maybe a couple of problems. But more or less, I'm planning to stick to the syllabus that's been covered in the class. Um,
Okay. Another question is related to the Mile-Nerod. So would you be covering that in slightly more detail compared to the pumping level?
yeah, is that in the, I mean, is that
In
coming up?
the week 3 it's there.
I see. Okay. Yeah, we can do that. Yeah.
Yeah. Thanks.
Okay, so I'll stop the recording for now and just wait back for a couple of minutes. Yeah.